This is the second part of lesson 2.3, key features of a graph. Okay, we're picking up where we left off, and so looking at this paragraph right up here about rate of change. So you're familiar with the concept of rate of change because we talk often about that as slope. Okay, slope is a rate of change. So the rate of change is a ratio, which means two numbers compared to each other. So like if the slope is 1/2, that's a ratio of 1 to 2. And that describes how much the rise is changing with respect to the run. So it's going to rise 1 for every 2 that it runs. So that's the ratio of it. If an equation is linear, it doesn't matter where you look to find the rate of change because it's a constant rate of change. So a slope is a constant rate of change. It does not change at all. So what I mean by that, if we come down here, if I have a line here, it's going to be a constant rate of change. If this slope is equal to 2, it means it's going to go, maybe that's a 2/3. I'm going to go up 2 and over 3, up 2 and over 3, up 2 over 3. It's going to be the same rise and run all the way through the line. Now, a non-constant rate of change would be something that goes like this. It's going to go steep and then not as steep and then steep or curved. And those rates of change are changing every time. So maybe from here to here, it's going to have a slope of 2/3. But then from here to here, it's going to have a slope of maybe 1/3. And then it gets steeper again. So maybe that's a slope of 1. And then here it's curving. And so where it's curving, it's like maybe from here to here, it's a flatter slope, and then it gets steeper from here to here, and then this rate of change would be different, and this rate of change would be different. And so this is a non-constant rate of change. So when we have something that is curved, that has a non-constant rate of change, so it's not called a slope, it's called a rate of change. And so we need to make sure that we understand the distinction. So when we say slope, we are talking about a linear rate of change that is constant. If we look at this picture, if a function is not linear, we can find the average rate of change within a certain area, okay? So this graph, I don't particularly like this graph too much because I feel like these two should be reversed. I feel like it's a little bit hard to read this graph because of that, but we're going to use it for this problem. So it says the graph at the right shows how long it took Alex to complete 13 homework problems. So let's look at the graph a little bit. So here's the end of the homework assignment, and it took 19 minutes to do 13 homework problems, okay? Now, does that mean that it took exactly the same amount of time for every homework problem? If it took exactly the same amount of time for all the problems, it would look like that. But because it's jagged like it is, that means that some problems took more time and some problems took less time. And as you know from your own personal experience, that's true. So it says, how long did it take Alex to complete 8 homework problems? So if we just look at the first 8, so make sure you're on the 8 problems, so the y-axis, and let's follow that over. How many minutes did that take? That took 14 minutes. Okay, now it says on number 8, for this assignment, on average. So that means an average. It doesn't mean like just from here to here because that's going to be different from here to here, here to here. Those are all going to be different rates of change, but it says on average, how long did it take Alex to complete a problem? So minutes per problem is what we're looking at. So minutes per problem. So since I'm talking about the entire assignment, I'm talking about what's the slope of that line. So how many minutes? It took 19 minutes to complete 13 problems. That is the average, and emphasize average, rate of change. So if you calculate a decimal for that, it's just a little bit over a minute, about a minute and almost a half per problem. That's on average. Some took longer, some took less, but that's the average for the entire assignment. Now, number 9, it says, how long did it take Alex to complete problem number 6? So let's look at problem number 6. She began problem number 6. Here's problem number 6. And she ended problem number 6 right there. And she began problem number 6 where she ended number 5. So this was problem number 6. And so for one problem to go from problem 5 to problem 6, it took how many minutes? So it goes 8, 9, 10, 11, 12. It took, nope, not 12. It took 3 minutes to complete problem 6. Okay, so remember when she completed number 6, she was done. So when she completed 5 is where we're starting to look. So that's why we're looking at this part right there. Now, if you look at a different part of the question, if I said, how long did it take her to complete problem number 10? Well, then that's different. So problem number 10, she ended it right there, and she began problem number 10 right there. So how long was that? That wasn't very long. That was a lot less time to complete problem number 10. So it just depends on the interval that we're looking at. So for this one, we're looking at the interval of problem number 6. Now, the next part says, explain why this answer is different than 19 over 13. How? Because 19 over 13 is not equal to 3. So what I'm asking you to do is explain why is 19 over 13 not the 3-minute average that it took her for that one problem. So think about that. Why would it be different? Okay, on the next 3 problems, we're going to go back to some previous graphs that we had. And so it says, find the average rate of change for the given interval. So for just from one point to another point, like we did with number 6 homework problem on the previous thing, we're going to find the average rate of change just for that interval. Leave as a reduced improper fraction. So if the interval or if the rate of change is 5 over 3, you're going to leave it like that. Do not turn it into a decimal. Do not turn it into a mixed number. So number 10, it says, look at example number 2. The interval we're going to look at is from 0 to 2. So let's go to example number 2 on previous page. So I put them here. So here's example 2 right there. Okay, so we're going to look at that. And we're going to go on the interval from 0 to 2. So what does that mean? So let me zoom in here a little bit and see if we can get this a little bit bigger. Okay, scoot it over here. Okay, so if I look at the interval from 0 to 2, so let me write from 0 to 2. That means I'm going to start my interval at 0, so find 0 on the x-axis, and I'm going to end my interval at 2, so find 2 on the x-axis. The easiest way, I think, to explain it is if you kind of take out your imaginary scissors and you cut, you're going to cut this strip. So this strip that's in here, that's what we're looking at. Throw the rest away. Those don't matter, okay? All we're looking at is what's happening in this strip. So inside of this, my graph is starting there, and it is ending there. All you're going to do is connect those two and find out what's the slope. So to get from point A to point B, I'm going to go up 1, 2, 3, and over 2. Up 3, over 2. So that is actually the average rate of change, not for the entire graph, because if we look at the rest of the graph, like over here, I'm not going to go up 1, 2, 3, and over 2. No, because the graph is right there. So that's more of a, like up, a little bit and over 2. That's not even very much at all. So it's just for the interval that we're talking about. So that's why it's really important that you understand how to find your interval on your graph. Okay, next we're going to look at graph A. So look at graph A. And so I'm going to come over here and look at this here. And it says that we're going to look at the interval from 0 to 3. So coming over here, I'm going to go into this graph, and I am going to start at 0, and I'm going to go 1, 2, 3. And so again, think about cutting this strip. So all I'm interested in is looking at that. I don't care about this. I don't care about that. All I want is that in the middle. So I'm going to look at where does my graph begin in that interval. So it begins right here. And where does it end in that interval? Right there. And I want the slope from point A to point B. I'm going to go up 1, 2, 3, 4, 5, 6, 7, and over 1, 2, 3. Up 7, over 3. So the rate of change on this one for that interval is 7/3. If I ask you about a different interval, it would be different. If I ask you about the interval from 0 to 1, that's going to be different. If I was to say from 0 to 1, I'm going to be looking at from here to here. So I'm going to be looking at from this point to this point. That's the slope of 1. That's different than 7/3. It means it's steeper if I look at the whole thing. So you just have to look at the parts that we're asking for in the interval. So don't look at the entire thing, especially if it's curved like you can't. Okay, for number 12, example number 1, we're going to look at the interval from -3 to +1. So looking at example 1, so from -3 to +1. And so you get your little imaginary scissors there and you just cut this off. I just feel like that's an easier way to think about it. But I'm going to start, you always start on the left, just like you read a book. I'm going from there. So I'm going to go from A to B. This is a negative slope. So it's going to be changing a negative amount. So we're going to go down 1, 2, 3, 4, 5, 6, 7, 8, down 8, and over 1, 2, 3, 4, over 4. So the slope is down 8 over 4, which reduces to -2. Okay, the interesting about a line like this one is it actually, with a line, it doesn't actually matter where you look. You can look at any interval on the entire line. I could say I'm going to go from here to here. And the slope is going to be from +5 down to -7. That's a difference of 12. And I'm going to go over from -4 to +2. That's a difference of 6. So down 12 over 6, that's also -2. So with a linear, because it's a constant rate of change, it doesn't matter where you look, what interval you look at. And so remember that about linear. It's constant. Okay, example 2 and example A, they were not linear, and so their rates of change are going to be average for whatever interval we're talking about. Okay, for the next problems, you're going to do a series of things. For each problem, you're going to do these next things. So let's just go through piece by piece. A, state the x and y intercepts as an ordered pair. So the x-intercept is where the graph crosses the x-axis. So here's the x-axis. Now look at what type of graph it is. It's an exponential. It's going towards the x-axis, but it's not touching it. So there is actually no x-intercept here. You're not going to put 0, 0 because it doesn't cross at 0, 0. And so there is no x-intercept there. Y-intercept, it does cross. It crosses right there. So that y-intercept will be at 0, 17. Okay, B, state whether the function is increasing or decreasing. So starting at the left, it goes down. So you're going to say decreasing. Do not just write D, write the word. C, state the domain and range using interval notation. So the domain, because it's exponential, if you remember I told you, think about the little guy walking along the sidewalk. There's always a graph, and that's going to be all real numbers. So you're going to say from -infinity to infinity. The range, how high does it go? How low does it go? So you need to figure that out. Now looking at this, it is getting closer and closer to 1. That's where it's going. So 1 is there, and how high does it go? Infinity. So my range, y is an element of, it's going to go low from 1, positive infinity. Okay, D, it says state the average rate of change for the given interval. Right as a reduced improper fraction. So the interval I'm interested in is from 1 to 3. So again, on the x-axis, these are always on the x-axis from 1 to 3. So I'm interested in where does the graph start and where does it end and what is the rate of change for that. So I'm going to go down 1, 2, 3, 4, 5, 6, and over 2. Down 6 over 2, which reduces to -3. And then E, it says write the equation of the asymptote if there is one. There is one here because of the type of graph it is. And so you're going to write y equals 1 because it goes through the y-axis at 1. Okay, on number 14, you go through and you try to answer all the questions right there and then come back and see if you got it right. Okay, here's the answer for number 14. Note that it is a linear equation. Because it's linear, we know the domain and range. We can see from looking that it's decreasing. You find the x and the y-intercept. I marked those in red. The x-intercept is at 2, 0. The y-intercept is at 0, 4. Remember that for the x-intercept, the y is always 0. For the y-intercept, the x is always 0. That's how it works on the graph. Okay, for the rate of change, I did that in green. So the rate of change, the interval from 1 to 4, so I made a little mark at 1, made a little mark at 4, and I went up and found the graph, went down and found the graph, and counted the rise and the run. It's going down 6 over 3, so that reduces to -2. And because it is linear, there are no asymptotes. Okay, you should now be able to complete your homework for this lesson.